In this video, we're going to talk about a concept called the weighted atomic mass average. So this is actually the reason why when you look up an element on the periodic table, they have decimal points after their atomic number, like carbon is 12.011. Now, here's the idea. You always round these to a whole number, okay? And that's still what we're going to do. And no one carbon atom is going to have a mass of 12.011. What that number represents is right here. Here's the key. It is the average. It's just like if you had a multiple choice test, right? If you had a 10 question test and it was all multiple choice, your score is going to be 1 through 10. No one's going to be able to get a 9.5, right? Because it's multiple choice and you either got it right or wrong. There's no partial credit. So how do you get those decimals? And that's the same with atoms. Their weights are whole numbers. There's no decimals. How do you get the decimal? Well, it's the average, and it's specifically a weighted average. So what that means is if I were to take, let's say, carbon 12 numbers, there's three types of carbon. There's carbon that weighs 12, carbon that weighs 13, and carbon that weighs 14. If I added them up and divided by 3, I'd get their average, 13. But that's not enough. That's a straight average. A weighted average takes into account the fact that there are a lot more carbon 12s than there are 13s and 14s in the Earth, essentially. And so you have all my carbon 12s. If I add all those up, this represents all of them. And then here's the carbon 13s. Maybe they're a lot less common, but not super common. And then here's the carbon 14, very uncommon. And then if I add those up and divide by the 11 numbers, I get a number that's 12.3, which is much closer to the actual weight of carbon on the periodic table. And if you think about that, carbon's mass is 12.011, so the amount of carbon 12s is going to be much more than this, but I didn't want to actually show you how many there were. Now, there is another way of doing this, so be aware. You could take, if you look at how many 12s there are, and this is how we're going to do it. So if you took all the 12s and you said, all right, there's 8 12s, you could say, well, that represents what 8 12s would add up to. 12 times 8 is the same as adding 12 8 times. And then there's 2 13s. And so, I mean, obviously they're easy to add together, but if these numbers were, let's say, thousands and millions and billions, then you wouldn't want to do that all day long. And so that would represent it. And then the 114, obviously we would never do this in real life, but what if it was like 1,000 of them? So you wouldn't want to do it that way either. And so there's your 14. And so that's one way of condensing the math. And so what this represents is the atomic mass average is the average mass of all of the naturally occurring isotopes. Keyword there. So in other words, by naturally occurring, we mean that if we take a hunk of carbon, which is like, let's say coal, it's something close, it's almost all carbon. So if we take a hunk of coal and we say, if we add up the weight of all the carbon atoms that happen to be in the coal, what is their average weight? And so that's what this represents. This represents the average mass of all of the naturally occurring isotopes. Now, for Earth, what's naturally occurring might not be the same as the moon. And so the weighted average masses could theoretically change if we were talking about different planets. But, you know, how often do we get to go to a different planet? So we don't bother mentioning that too much. And we say the most abundant isotope is the one closest to the weighted average, which makes sense. If I told you the average was, if there were 3 scores you could have gotten on a test, 12, 13, and 14, and the class average is a 12.3, well, that means most people in the class got a 12, okay, which means there'd be more 12s in the average than 13s or 14s. If the average was, 13.9, then we would say, well, most people in the class got a 14 because that's the only way you'd have 13, something so close to 14. And so when we look at carbon on the periodic table, the atomic mass is this, and so we would say that carbon 12 is the most abundant because that average is closer to 12 than 13 or 14. And that's pretty much it. Here are the steps. They're pretty easy, and I explain them. I'm going to do some problems with you, and then that's it. So let's look at this first one. It says the element copper has naturally occurring isotopes with a mass of 63 and 65, and a relative abundance and atomic masses are 69.2 for mass 63U. Notice U is the unit for AMU, and 30.8% for mass 65U. Calculate the weighted average mass of copper. All right, hopefully I have a calculator. So for this one, we are just going to multiply the mass by the percent. So since it's 69.2% for this mass, I'm going to multiply those together, and it's 30.8% for this mass, I'm going to multiply those together, and then I just divide by 100. And the reason, well, I'll get to it in a second. So it's going to look like this. 69.2 times 63. Then I'm going to add up the next one. Add it all up, divide by 100, and I'm going to get an answer. And the reason I divide by 100 is because these are percentages. And so think of it this way. If you had 100 atoms, right, 69.2 of them weighed this, and 30.8 of them weighed this, if you wanted to find their average weight, you would just add up this number this many times, and I'd add up this number this many times, and then divide by 100 because there were 100 atoms, and that's why it also is an easy way to convert percents back to decimals. So that's essentially what the dividing by 100 does. And then we get our answer. Now, before you do your answer, think about this for a second. The bulk of it, 69.2%, weighed 63. A much smaller amount weighed 65. So should your answer be closer to 63 or 65 is the question. So when we do this, and we end up with 63.62U. Now, it makes sense because there's more of the 63 weight than the 65 weight, so therefore the average should be closer to 63 than 65. That's something that you should really ask yourself because it's a really easy way of figuring out if you made a mistake. All right, so that's first problem down. Next one, they tell you that 10.2% is bromine 78. Now we know from atomic structure that bromine 78, the number 78 after the name of an element, tells you its mass. And 10.6 of it is 79. And 79.3, the bulk of it, is 80. So right there, I can now say, all right, I know my answer is going to be closer to 80 than 78 and 79 because it's a way bigger number. So we set up our problem, 10.1 times 78 plus 10.6 times 79 plus 79.3 times 80. Add it all up, divide by 100, and let's see what we get. $79.69. Could be 692, but whatever. So this is the one type of problem where rounding matters, because if you look at this, normally I don't care about rounding. This is the one time I'm going to care about rounding, because whether your answer is right or wrong is literally going to be dependent on typically the first number or the first two numbers after the decimal. So for these, I really don't want these numbers rounded at all, because then I can look at it and see if you really did it right very quickly. This one's an easy one. Boron has two isotopes, boron 10 and boron 11. Which one is most abundant? Explain your answer. Well, without the weighted average mass, I wouldn't be able to know my answer. But luckily for me, I have a periodic table which tells me these things. So I go to the periodic table, I go to boron, its weighted average mass is 10.81. So since the weighted average mass is 10.81, which one is that closer to? And the answer is boron 11, and that's the reason why. Last one. There are three isotopes of silicon. 75% is 28. And the reason I know it weighs 28 is you can see right here, that's the atomic mass spot. So 75 weighs 28, so those two. And then 13 is 29. And then the remaining is silicone 30. So normally we would say something times 30. But we can solve that for that 30 easy. We know the percents have to add up to 100. So 75 plus 13 is what, 88? So therefore the remaining 12%, because that's how much more I'd have to add to get to 100, must be 30. And then when we do the answer, divide by 100, And I should get an answer closer to, should be able to predict this as well. I should get something closer to 28 because the bulk of it's 28. The biggest problem students typically run into with this is when you're plugging all this stuff into the calculator is not using your parentheses right, or putting in a multiplication sign where you meant to put an addition sign or reverse. And there you go, and it's exactly what we would predict. And predicting the answer is a good way for these types of problems to make sure you're doing them right, because if you get an answer and it's like wildly off from what you predict, there's a chance you probably made a mistake in your calculator. So what I would recommend is you go back and you double check the math on that, because these are typically very predictable, and you're not typically going to get more than like 3 isotopes. Maybe you might get a problem where you get 4, but I've never seen a problem where they give you more than 4 isotopes. There's really not much of a point.